here's where things get interesting. Up to this point, addition and even scalar multiplication has seemed pretty straightforward. Just the same type of operations we do in regular plain old arithmetic. However, now comes multiplication, where things actually get very confusing very quickly. With that stated, it's still not a difficult operation if you just take the time to learn it. Now, what I have in the notes is a step-by-step procedure on how to go about doing it on a larger matrix. And I advise that you read through those set of notes because I go through element by element and show you how to do it. With that stated, I'm going to briefly go through matrix multiplication here. Okay, now, with matrix multiplication, there is a requirement. And the requirement is not the same as matrix addition. Recall, matrix addition needed, if I had a matrix A, where I had the number of rows by the number of columns of A, and if I had matrix B, number of rows of B by the number of columns of B, these two quantities basically needed to be the same, and therefore I can add them. Matrix multiplication is not the same requirement. Matrix multiplication necessitates that for the number of columns, the number of columns of A need to equal the number of rows for B. Now that looks strange, but just stick with me for a moment. If I have two matrices such that this holds true, the way that I define the ijth element of the new matrix that I'm constructing by multiplying the two matrices is defined as the dot product of the ith row. Okay, this is a vector. Okay, it's a row vector of the ith row dotted with the jth column. This is a row vector. This is a column vector. That's why this needs to hold true, because for one row, it will have MA columns. And for one column, it will have NB rows. And therefore, the two are the same, and we can go about finding the dot product. Put differently, or visually, if I have, let's say, just a matrix that looks like this, and a matrix that looks like this, notice that this is a 3x3 matrix, and this is a 3x1 matrix. And what I get out as a result is a 3x1 matrix. As strange as that sounds, but here's why. For the new matrix, this quantity is the dot product. This here is the dot product, or the inner product, between this row and this column. This quantity here is the dot product between this row and the same column. This quantity here is the dot product between this and this. And that's how we find it. Let me give you another visual example. Suppose we had a 2x3 matrix. Draw that out a little better. Multiplied by a 3x4 matrix. So this is a 2x3, and this is a 3x4. Because the columns here are equal to the rows here, number of rows, we can conduct multiplication. And what we get, by the way, is a 2 by 4 matrix, okay? So the first element is the dot product between here and here. The second is the dot product between here and here. The next is the dot product between here and here. The next is the dot product between here and here. Then we go down one row. The next is the dot product between here and here. The dot product between here and here. The dot product between here and here. And the dot product between here and here. And from that, we get a new matrix. I'm going to go through one small example to illustrate this. Suppose that we have the matrix A, 2, 3, 4, 1, and we have the matrix B, which is 2, 1, 1, 1, 0, 5. Because this is 2 by 2, and because this is 2 by 3, we see that these are equal, and therefore we can multiply. And we get, as a result, a 2 by 3 matrix. So let's do that. First one, dot product between here and here, which is 2 times 2 plus 4 times 1. Next row, next entry, here times here, where we get 2 times 1, plus 4 times 1. Next one, here, dot product of this and this, 2 times 0, plus 4 times 5. Okay, now we move to the second row. And we do the same thing we did before. 3 times 2 plus 1 times 1. 3 times 1 times 1 plus 1 times 1. 3 times 0 plus 1 times 5. And when we do the arithmetic on all those individually, 4 plus 4 is 8. 2 plus 4 is 6. 0 plus 20 is 20. 6 plus 1 is 7. 3 plus 1 is 4. 0 plus 5 is 5. And that is A and B. Now, I want to be very clear here. Unlike multiplication, where it is true that A plus B is the same as B plus A, and unlike scalar multiplication, where this is true as well, although a little weird, but that's okay. All of that is all good and fine. However, it is not true in general that this is the same. Put differently, the operation of matrix multiplication is not commutative. So, and you can see that, right? Because if we were to flip these, suppose we did B times A, then what we're doing is multiplying a 2 times 3 matrix times a 2 by 2 matrix. And what we get are incompatible matrices because these are not equal. So if we have an incompatible matrix, then we're not going to get the same results because we can't multiply them by definition. I will admit that this takes a lot of practice. This is not easy, but after a while, you can kind of do it in your head. That sounds strange, but it just takes some practice. So go through the notes where I have another example point by point laid out over the course of, I think, 10 pages or something to that effect. and try to work through some other examples to just get the hang of multiplying the two matrices together.